Good evening to all. Am I audible?
Yes, I can hear you.
Okay, now welcome to the fifth day of our faculty development program. As we approach the culmination of this enriching journey, today promises another series of insightful sessions and engaging discussions. Let's continue to build on the knowledge gained, fostering collaboration and innovation to advance our teaching practices and professional growth. Now, it is my great honor to introduce our esteemed first speaker, Mr. Kumar Vishal. Meet Kumar Vishal, an accomplished AI architect with over 14 years of experience in software design and development. A visionary in the fields of computer vision, deep learning, and machine learning, Kumar has spearheaded cutting edge AI systems that blend innovation with practical applications. With the master's degree by research from Triple IT Hyderabad and a wealth of professional expertise across global tech gains like GE Healthcare and Samsung, Kumar excels in delivering transformative AI solutions. His portfolio includes advancements in predictive maintenance, luxury items, authentications, and groundbreaking traffic light recognition systems for autonomous vehicles. Notably, his patented work and research publications reflect his dedication to pushing the boundaries of AI technologies. Beyond his professional achievements, Kumar actively contributes to the AI community, mentoring emerging talent and exploring innovations in generative AI. Please join in welcoming Kumar Vishal as he shares his insights and experiences in shaping the future of AI driven technology. Welcome, sir.
Oh, thank you. Thank you, Millie. Hello, everyone. My name is Kumar Vishal. Thanks for the introduction. So we'll jump to today's session. Let me share my screen. So let me know if you can see my screen.
Yes, it's visible, sir.
Okay, fine. Great. Thank you. So thank you all. Thank you joining. We'll be going to introduction for the transformer, which is a combination of cerebral attention and the other phenomena. So we will be covering these topics in stages, and we will be covering in such a way that we are kind of inventing the first time. That's called a first principle learning. And I will be stopping in between for the questions. And let's start. So let's start with the why. Why exactly that there was a need for the transformers? What exactly pushed to the transformers? So before transformer, I think there's a architecture called RNN, and the RNN was a widely used architecture for the most of the NLP related tasks like sequence to sequence translation or sentiment analysis. So RNN was the one of the basic architecture which was used. So it is basically has a two blocks, which you can say encoder block and decoder block, and this is the basic things. So what happened? There was a fundamental problem with the RNNs. Can you please, sorry for this. I'm really sorry for the interruption. Yeah, so fundamental problem with the RNN was like once any sentence or any task which is more than 30 words, the performance of the RNN starts declining very drastically. And there's a feel of that we should need of some better architecture which can help for the longer sentence and everything. So let's see how it exactly goes on. So we will have a quick review exactly how the things work. So let's think about this NLP thing. So NLP is like words, sentences, and everything. So NLP, we have a very big thing which is combination of words, and how exactly a word has to be communicated to the computer. So we have to really represent a word in some numbers, right? I mean, right, the computer is not going to understand, hello, how, all those kind of text. So we have to represent those words in a number. So there were the different ways. We started with the hot encoding. It is just a quick review, TF-IDF, and then finally, before transformer, there is a word to vec, which was one of the most advanced technique to represent any word into a number vectorization. So that's called those things. So how exactly it looks like, the embedding looks like. So what happens? So for example, you can see uh, any word to vec, how it represents. Let's say you have a king and queen, and that algorithm, represent the king as a set of numbers or vectors, what we can say. So the vector embeddings are used for vice versa. Sometimes we say vector, sometimes we say embedding. So both are the same thing. And the good thing was this representation was every dimension. So there's currently we have king in a 3 dimensions. So every dimension has some latent meaning. So we can say, like king. So maybe first dimension represent wealth. So for example, king is a very, wealthy person or something like that. Queen is also very close to wealth. So we can say these values are pretty high, close to 1, right? Then you can say there's a third dimension, which is like represent masculinity. What is your gender? So the king is a male, so obviously there's 1, and the queen is female. It's a very low value, 0.1 or maybe 0.1. So that's become a very intuitive way to present our words in a vector form. So, but there was a problem with this. There's a problem with this, that these words was average meaning of from your data set. And what exactly it means, as you can see, we have a lots of sentences in our data set, like an apple day keeps the doctor away, apple is healthy, apple is better than orange. Now finally we say apple makes a great phone. So obviously as a human we are so good in NLPs. So we know all first 1 to 3 years used for apple as a fruit. But in the fourth sentence, we automatically know Apple is not, we're not talking about Apple as a fruit. We are talking about Apple as a technology, Apple as a company. So this kind of context aware was absent in the word to vec thing. Because what happened, let's say we have a 10 case, 10,000 sentences. And out of those 10,000 sentences, we have only 9,000 for Apple and fruits for 1,000. So we have a very huge disbalance between our data set. In the one context where the apple is used as a fruit as a very high number, and where the apple as a technology is a very less number. So overall, what you will say, the embedding will be something like this. Let's say we have a 2-dimension embedding for the apple. So this will be representing fruit, this will be representing technology. So they will say the 0.9 is for the fruit and 0.1 is for technology. But what actually we want is, when we are talking about sentence number 4, we should expect that this technology weight should be more and the fruit weight should be less. It should be vice versa. So this kind of intelligence was not there when we are talking about word to vec embedding. So yeah, that's we have talked about. So what should we do? So here comes a picture of a self-attention, one of the basic block of your transformer. So what self-attention does is, it takes a big, static embedding. So static embedding generally represented as E. So whenever you say E underscore, you can think as a static embedding. And this will go to your self-attention block. And what the output is the context-aware embedding. So what it means is, when I will put my Apple makes a great phone into self-attention block, I can expect embedding 0.1 at a fruit and 0.9 as a technology. So what so it's a kind of thing. That was the expectation from my self-attention block. So that is what we call context-aware embedding. So my my embeddings are aware that what context we are talking about. Okay, great. So for example, again, let's say sentence 1 is money bank grows. Sentence 2 is river bank flows. As you can think easily, in sentence number 1, bank means our normal money banks, SDFC, SBF, whatever. River bank means simple river bank we are talking. So how should we go this kind of phenomena? How should we really come with this things? Let's start a very simple thing. What if we take an average of nearby words? So let's say, for example, we say the embedding of money will be the weighted average of the nearby words. Average embedding of bank will be the weighted average of nearby words, right? So once we do this, as you can see, automatically our embedding will be the aware from the context. Okay, what is my nearby? We are the nearby, what is the technology? So we have a weighted for that. So looks okay, looks great. So we have a very simple phenomena has able to tackle this context aware problem up to good extent. But there is a small thing. What is the small thing? Let's see. So these weights has come 0.7, 0.2, 0.1. Now I have manually put this weight. How should we find these weights? How should we know what exactly these weights should be? So one way is to think of like, if we take, there's a one vector, there's other vector, and if you take a dot product between those two, right? So that will be give a weight. Fine. So what exactly what you want to see is something like this. So this is a little bit a big jump. We will go slowly over this. So what we say is, what we say is, we take this word, money, bank, grows. We take this word, we take a dot product with this, we take a dot product with other word, we take a dot product with other words, and push to the softmax function. And I hope we are aware that softmax function does nothing but normalize data to 1. And we get the weights. So which is, if you can see, these weights are sum to 1, these weights are sum to 1s. So yeah. So what we do is simply we take a dot products between the different words, put that dot product into softmax function, we get a weights, and that weight is just simply, again, you multiply the way we are multiplying here, you get the things. Great. And we are done with this, right? So simple dot product between the vectors will give you those weights. Now again, what is the good thing with this? What exactly we have achieved here? If you think, we are able to find those weights in a very quick and fine, because dot product is very fast. You can do those dot product in a milliseconds or something like that. Other thing, as you can see, there's no reason that all the weights cannot be parallelized, because, for example, if I talk about money, we know the embeddings for the money, we know the embeddings for the bank, we know the embedding for the grows. We can have this parallel, we can have this parallel, we can have this parallel. So all the process can be parallelized. We don't have to very, wait for the sequence. So that is what it means. You say e-money, there's the same thing, n cross 3. I got this matrix, we got softmax. Again, you multiply. It is more of a matrix formalization, what you just see here. And we got our context aware embeddings. So operation can be parallelized. Great. But there is some cons also. What is the cons? So the cons, if you see, there's a no learning parameter. Till now, if you see, there's a nothing I have introduced which depend if we are aware of the normal mechanism of any neural networks, there's always some weights and matrices which learns over the time. So what happens if you see there's a no learning parameter, and what exactly it means, what is the problem? So think about a sentence which says, how are you? The Hindi translation will be tum kaise ho, which is perfectly fine. Now, if you think about the English, piece of cake, what should be the Hindi translation? Generally, when we see a piece of cake, it's more like a metaphorical thing. What it means is it's a very easy task. But if you go with this, it will be like, if this logic, so the piece is different, piece and cakes, all the embeddings will be there. And the answer will be, whatever, cake ka tukda. That's what we call it. Piece means cake, like, whatever. Tukda, then cake, and all those kind of a thing. So the thing is that my context aware embeddings is good, but they still lack in some cases, like not able to learn with my data set. For example, even I have some data set where it means piece of cake means asan kam or something like that, but there is no way that I can train my embeddings that I should learn. So what should we do now? So let's see. So this is the paper where this attention is all you need from me, where I have taken. So I will highly suggest you guys to go there. So this is the taken from those papers. What they said, I will take my e-money, if you remember, again, this is simple word to make, and I create 3 embeddings out of that. So they call it query, key, and value. How these embeddings are created, I will come to that in soon. So query, key, and values. We have created 3 embeddings out of that. Let's see how it gets. So there is a very limited ways to create a new vector out of a given vector. So simple way, what we do is we have introduced 3 matrices. You can see this is my E bank. I have introduced 3 matrices, WQ, WK, and WV. You can see here, and I simply multiply, and I got a 3 new vectors. That's called query, key, and value. So I'm able to achieve that given a static embedding E bank, I can generate 3 vectors out of that. Okay, now let's see how it's really help us. So now what I will do, so this is the same thing, and I have to do this for all of them. And one important thing, the matrices which you are looking here, WQ, WK, WV, is shared for all the words in the sentence. It's not a difference. All of them share the same weights and matrices. So E money is there. E money goes to WQ. We got a Q money, K money, V money. Same thing. Everything will goes on, right? And what we do is we take a Q money, we multiply by the K money. Same thing. We will take Q money multiply by the K bank, Q money multiply the K money, and whatever the weight comes, it goes to softmax, and I got this values again. So how it help us? What exactly it does? So let's see. What exactly it does is we have introduced these weights. Okay, if you see in this process, we have introduced these weights. Now, when the weights are there, we have this ability to learn, right? We will see how exactly those things will learn. We have ability to learn the context of my embeddings. So till now, there was no weights. These are the random weights which we have initialized. And over the time, I can learn this. If you see, before, until these weights were not introduced, let's go back. There was no way I can really learn here. As you can see, there's no weights here, which I can learn. With the help of this, weights which has been introduced, I have generated some more, vectors, and those vectors will be learned with the help of my data set, right? And the hope is when I'm learning, this kind of error will be taken care, because now my embeddings will start depending on the data set, and the simple backpropagation algorithm will come into the picture, and things will be fine. So this is in the paper, this is how they define, attention. Fine. So attention is nothing but Q. We just say how we got a Q matrix, K transpose into V. Simple, nothing very, and thus these goes, just ignore this under root DK for some time. As you can see here, there's a nothing very, out of the box formula is here. The same thing which we are doing here, right? What you're doing is you're taking Q, transpose of that, multiplying, going to softmax, and again you're multiplying by the V value. So you can see here, Q multiplied by transpose, and this whole thing is multiplied. Now this constant come into the picture. Why exactly? What exactly it help us? So it help us with this. There's a concept in this machine learning that you can have this intuition. The higher the number of dimension in the vector, the variance in those vector will be even high, right? For example, if something is a very small, that's 2 number, and randomly generating between 0 to 1, so the variance between these 2 number will be very less as compared to if the vector is 512, right? So this is just a way to scale your vectorization such that the variance remains same irrespective of your length. So whether your vector or embedding, whatever you want to say, whether it is say a size of 512 or 100, once you simply divide by this under root dk. Dk is nothing but the dimension of your vector. That the variance get compensation. So this is just a scale factor, nothing more of that. Okay, so till now we have done with the self-attention. There is small more advantage in the what it has done in the paper. So the next step is a multi-head attention. So multi-head attention is a very similar to self-attention. The intuition behind the multi-head attention, as you can see, is what we do is we really simply break our q, k, and v vector into the parts, and the hope is each part will try to capture different meaning, and finally we just simply concatenate at the end of. See, it is simple, right? We have say for example, we have 512. I hope 512 is divided by 3. No, maybe something. So what we do is simply divide into 4 parts. Yeah, and each part will go into same kind of a calculation, simple, same calculation, and whatever the calculation we get, you say this head, simply again concatenate, and we get this matrix out of that. So idea here, what we do is, because we want to capture different meaning of our words, because NLP word, a same word can have a different meaning, like for bank, all those kind of a thing. So hope is, if I have a 512 long vector, some part will capture other meanings, some capture other meaning, all those kind of things will be there, right? So this is the one phase. Do you have any question before we go into the other phase of other details? Okay, I assuming, yeah, hello.
Not right now, sir.
Yeah.
You can
So,
continue.
okay. Thank you. So I'm assuming no questions. So other part, if you think, is that's called position encoding. So what exactly the position encoding trying to address? So position encoding is, as we know, the order in the NLP is a very important. For example, as you can see, Kumar killed a lion. That is the one thing. Other things, lion killed Kumar. It is just a jumbling of the words which make the meaning of the sentence totally different. Until now, if you see, there is no way that this whole architecture is capturing those encoding fashion. Like, it is simply, for example, if you say Kumar killed lion in this block, right, we'll get exactly the same final output, or you say lion killed Kumar. There's no difference going to be there. So currently we don't have any mechanism to capture the position of the words coming into the picture, right? So that's the reason they have introduced the positional encoding phenomena. So let's see how exactly they do. So what they do is, this is an example. Your cat is a lovely cat. So this is my first embedding. First embedding is nothing but your simple static embedding. Then they generate a positional encoding. We will see how exactly this is being generated. This is a simple formula. And you simply add those things. You add what, first row, second row to get a third row, first row, get a second, third row. So this becomes the positional aware encoding, where my, the order of the word is getting captured. How exactly we do that? So this is a simple formula. How this is being calculated for the even, as you said, 2i is an even position. For all even position, start with 0. So all even position, we use this formula, right? So I is the index here, and position POS is this index here. This index, like what first position, second position, third position. I is like 0, 1, 2, 3, something like this. For the odd position, we have this formula. So you simply calculate this value, and that becomes your this positional embedding, your word to vec embedding, and you simply add those things. Mind here, both have the same dimension. So we get a final input, and which is have this sense of capturing that what is my word order. Now the second question can be here is, like, they have told why this sine and cos function has been used, why not any other function. So they have plotted this position and depth phenomena, and you can see, as a human, we can clearly see some patterns here, right? What is the position, how this position is going. And idea here is, if we can see some patterns, so that pattern can also be learned over the time with the help of our neural networks. That's the idea of a whole this position encoding thing, right? Okay, so we are jumping to the final architecture, into how exactly about this transformation is built, how, what are the steps, and how a small training and inference part will be done. So if you go and see in net and where when even the paper, you will see a broadly these diagram of a transformer architecture. So we'll take at a very step-by-step mechanism, and we'll try to see how to. So let's not boggle about this so complicated diagram. At least we can see this is the one part and this is the other part. So this one part is called encoder, simple thing. The other part is called decoder. This is, and let's say this whole thing is a one very basic block of transformer architecture. Simple. Now what next? As you can see there is an X. What an X exactly means? That the same encoder block is repeated multiple times. In the same way, the same decoder block is repeated multiple times, right? So from very simple blocks, we are trying to even go more depth. How many times? In the paper, they have written it 6 times. So I hope this is also 6 times. Yeah, there's 6 times. We repeat this the same block 6 times. Now let's go a little bit deeper in the encoder block. So what does encoder blocks contain of? There is a self-attention, which we have kind of gone through. Self-attention or multi-head attention, which are very correlated. For the simplicity of the discussion, we will try to have the self-attention blocks. Multi-head attention is nothing but a one step, simply breaking those into small parts, again combining them. So for the simplicity of discussion, we'll talk about self-attention. So each encoder block is a consist of a self-attention and the feed forward, simple neural network. As you can see here, this is like, multi-head attention or self-attention followed by a simple feed forward network, that is add and now. Okay. So this is how it looks like. My, input will be here. This first block, second block, third block, fourth block, sixth block. So the previous output will be act as an input to the next block. And this output of the final goes to the decoder block. Right? Simple. We'll go more depth. So let's see how exactly your input get ready. How exactly, before we even go inside an encoder block. So let's say I have this how are you. So this how are you first get tokenized. So the how exactly that get tokenized is out of this discussion. You can you can imagine something like that each number is given to some ID kind of a things. For example, let's say ID how is given some 23, R is given 42, all those kind of a thing, right? We tokenize those things. Those token is converted to static embedding. So as I said, whenever you say E, this is more like a static embedding. That is a thing, right? So what we achieved here, we have started with simple text, we tokenized, and we end up in a more of a static embedding. Great. What next? We got how are you tokens, embeddings. These are my embedding. If you remember, we have introduced the positional embeddings here. So positional embeddings is nothing but these embeddings which we have calculated. As you can see, this is my positional embedding. We have introduced this positional encoding here. Both get sum and we get this input is ready. So this is the basic first input for my encoder block, right? So let's see how it goes into that. So this is my input, right, which goes to my multi-head attention, and the output is again my Z1, Z2, Z3, and this input is also passed more like a residual connection. I'm hoping we have session regarding the residual connection in the past lectures. It is very similar to this res connection, res architecture. So where we pass this thing and we simply add output and this input as a res connection, and that is go on to the next step. So what happened? We have this input, we got this output, right? This is the residual connection, then goes to layer normalization, and we got my first Z1, Z2, Z3 norm. So what exactly it is? Let's go back and try to have a look. Yeah, if you see, right, multi-head connection. So first is this is my input is ready. I put into multi-head nothing but the Z1, Z2, Z3. There's also a skip connection you can see here, right? So all X1, X2 is again going there, and those are getting added with the add and norm. So first we add and then normalize. So let's see again. The input goes here. This is my residual connection, layer normalization, and simply add and norm. So we got this one normalized vector. Fine. Okay, so far we have done with this below block. Multi-head, add and norm, we are done with that, right? So we got Z1 norm, Z2 norm, and Z3 norm. Simple. Now next is a simple neural network. right? So what we do is you simply stack my Z1 norm, Z2 norm, Z3 norm, which is become 3 cross 512 matrix. After saying there is a feed forward network. This feed forward network, nothing but a simple neural network, which is the size of 512, 2048, and again 512. So this is added to get more of the non-linearity, so that the architecture is capable to capture more complex patterns and all those kind of a thing. So we add simple this nonlinear things, right? So we have this, if you can see, we have this, final input ready thing. Then we have got Z1 norm, it passes, layer normation, and we got Y1 norm. Now this is my final output, as you can see here, which is again ready for the next block output, or we can see, right? So whatever is coming out of this is an act as an input to others coming block, and will keep on going at least 6 times. So it will repeat again and again and again. Same phenomena. First multi-head, then add a norm, then feed forward, and all those kind of things will keep on going. Coming to decoder block. So first, before we jump, let's see where are we exactly. So we have passed all these 6 blocks, and we are going to decoder block now. Okay. Yeah. So coming to decoder block. So decoder block has a one block which is we have not discussed here. I think that's called masked multi-head attention. So what exactly this masked multi-head attention? Let's see. So whenever we get outputs, right? Till now we have find that okay, whatever the output we get is more like a weighted average at a runtime. So it's possible, just say for example, say aap kaise hain. So aap kaise hain is like 0.8, 0.1, something like we'll get it, right? Now what you can see here is all these equation 1, 2, and 3. That at the runtime, all these things are available. So for example, I say, how are you? The output will be aap kaise hain or something like that. At the runtime, I have all the data, right? But when you are testing or inferencing, there's a no reason when you say aap, then the machine also knows what is my next word, kaise. If it is not clear now, we will go through that. Let's not curious about that at this stage. So we'll see why exactly this is important. So assume whatever you given to you, this aap kaise hai. So this aap is not aware what is my next word. In the same way, kaise is not aware what is my next word when we are inferencing. But at the train time, it is available. So what happened? There's a concept called data leak. If you give some data to your architecture at a train time, which is not available for you at the inference time, that's become a data leak case. So you can imagine more like a given exam, right? And if some data is available at when we are preparing for exam, and at the test time that data is taken out, obviously we are not intuitively we are not going to do good very at the test time, because there was some support which was given when we are preparing, and that support has been taken off, right? This is, can you please mute someone? Yeah, thank you. Right. So what we do is mask multi-head addition. If you remember, there is a score thing, right? So we mask this part of things. So for example, your can see only your, and all this data should not be seen by the your. Cat can only see your and cat. All this correlation should not be seen by the cat. So we mask upper part of my weight. And how exactly we do that? We got this, if you remember, scale square t. We take a matrix, simply add with minus infinitive. This becomes my weight space minus. When you go to the software function, so minus infinitive software function becomes 0 automatically, right? So we simply put a mass matrix which help me to curtail the upper part of things, so that at a training time the data link is not there. For example, your is not able to see the cat is not able to see the is, all this kind of thing. So let's have a quick exactly how this training is done, right? As you can see, there's some sentence, which let's say there's a simple task of translation from English to some, I don't know, maybe French or Italian, whatever. So what we do, we start with the append a start of sentence. SOS means start of sentence. EOS means end of the sentence. So we send it from here, and the same should have a label data. What is T, Yama, Molto, whatever we have sent from here. Data goes here. All those standard things which we have discussed will keep on going. Encoder block and all those 6 blocks will give. Whatever the output comes, it comes here. Decoder goes at the same times. The data from the here goes. And it is supposed to predict this T Yama Molto. And whatever the error, I hope cross entropy losses work here, whatever the error is there, and that is again feed forward. So back propagation is there, and that is again all those weights are keep on upgrading with the help of back propagation phenomena, right? So this is a basic training. This is a very basic training of any neural network is gone through. This is also the transformer also gone through this thing training. The catch is in inference time. How exactly the inference works? Let's see. So let's say I have this sentence which say I love you very much, and I have to find what exactly how to execute this work, because at the inference time or test time I don't have a output, right? So first I send this, whatever the final vector will come out of this, and I start with SOS, which is a start of my sentence. This is the first thing I put into this. I come here, and it is supposed to give me the T, because the correct answer is T Yama Molto. So I know I start with SOS, and it gives T. That's my time step 1. What happened at time step 2? Whatever the output of my decoder block, and from the encoder which we have already computed. So I will not compute the same vector again and again. So I will take this, and I will, whatever the output of the previous block, I append SOS and T. It will again go, and I'm supposed to give AMO. AMO will come into the picture. It will say Molto. When Molto come into the picture, it should say end of sentence token. So whenever the end of sentence token is achieved, I will say, okay, fine, my basic task is done. I've achieved the task. So now you have this intuition why this masked attention is required. Because at the inference time, you see, right? Because there is no way I can see, I love you very much, all the sentences at the same time, because I'm going step by step, right? So that is the reason that the masked attention is required in the decoder part. Okay, so there are a few references. These are very good references, I will say. All of the materials, images has been taken from these references. I will highly request everyone here go through this and try to have a look. Thanks. We have any questions here?
Participants, if anybody is having any question, please ask, or either you can put your question in a chat box.
Dear participants, hello, am I audible?
Yes, you are audible.
Hello, am I audible?
You are audible.
Yeah. Okay, any participants have any question can ask? Or you can put your question in chat box also.
No problem. You can feel free to mail those questions. I will definitely come back on those things. If you don't
Anyone?
Anyone I have a question.
Yeah, sure.
Yeah, Vishal sir, I have a question. So, what basically the role of self-attention in a transfer model?
Okay, so role of self-attention. Okay, let me just share is, okay, it is shared, right? Go to the basic thing. We can go in details as much as you want, but basic thing at a very high level, there's a problem with the embeddings, right? Because it is not context aware. Correct.
Okay.
So, example, Apple makes a great phone. So suddenly it won't turn that, we are talking about the Apple company, not the Apple fruit. So what self-attention does is here, is it give you a context where embeddings where we know that when we talk about Apple makes great phone, that we are talking about the Apple company, not the Apple phone. For example, if you see here, this is the embedding for the apple, which, let's say, this is fruit, this dimension symbolize fruits, and this dimension symbolize technology. So obviously when I say out of 10,000, 9,000 is sentences related to apple, so it will be automatically inclined towards the fruit, right, in a simple word to way, and it will imply very less to technology, right, because as you can say, most of sentences belongs to fruit thing. But we are not supposed to do that. We are supposed to do that whenever this Apple makes great phones, the embedding should reverse. It should be like 0.1 and 0.9. So if we have a self-attention, so the idea is if you pass Apple through a self-attention block, you should get 0.1 and 0.9, not 0.9 and 0.1. So it if I say put it very briefly, word embedding, so self-attention blocks generate a word embeddings which is aware of the context. For example, apple as a fruit or apple as a technology.
Okay.
Yeah.
Okay. So
Okay.
one more question from the Anurag Gupta side. What does the acronym word a transformer based model stand for?
Acronym
Bird,
word.
BERT, bird. Huh.
I don't remember. It's something bi-directional, but you can easily find it on the. I mean, this is just acronym, right? Some bi-directional encoder representation bird, right? That's all.
Okay, no issue, sir.
Yeah.
So I have a question.
Yeah. Go ahead.
How does positional encoding help in transformer models?
Okay, so I think we have briefly discussed this. Let me just tell you again. So, for example, you see this money bank, not this one.
This one, I think.
No, not this one. Yeah. You see this Kumar killed lion or lion killed Kumar.
Yeah.
So, right. So, if you see as a word, all the words are same. There's no extra word has been introduced here, right? But the meaning is totally different. Just because I have changed the position of the words. Right. So the positional coding, nothing, it tried to convey that, the position of the words which has been used in the sentence so that your architecture can learn the meaning. So because first word say Kumar killed lion, I mean Kumar ne lion ko mara. Second, lion killed Kumar. There's very opposite things, right? But till now, there's no way I can find out here. There's no way I can find out here which word has come first, which word has come second, and what was the same thing like that, right? So here the position encoding comes into the picture, which try to put the data that what is the order of my word. For example, if you see here, right, both POS, this is a function POS and 2i. So POS is like what is my position. For example, let's talk about position as of now, this position variable. For example, position of the Kumar is 0 in the first word, and the position of the Kumar in the second word is 2, 0, 1, 2, 0, 1, 2, right? So that will have a very different encodings, and that's the role plays by position encoding in this whole thing. I hope I answered the question.
Yeah. Because, sir, thank you.
Yeah.
So one more question from the Millie side. Name 2 popular architectures based on the transformer models.
So there's a one encoder model, one there's decoder model. For example, GPT is the more like a decoder models. So for example, what they do is like for example, BERT is your encoder based architecture, right? What someone has asked. GPT is a decoder based architecture. Is that what context you are asking, or I'm to be able to, I didn't get the question very clearly. So architecture as in what architecture you are asking? Hello.
She asking 2 popular architectures based on transformer models. Any 2 architectures. There is not
Like you
not a
can take
defined
BERT, then you can take BERT and GPT. Those
word
are very
and
different architecture.
okay. Okay. Thank you, sir.
Thank you.
Nisa, one more question of the Anurag Gupta side.
Okay, no, please go ahead.
What are the key hyperparameters that need Turing in transform models?
So I will tell you, there's a very good thing with the transformer models. They are very stable in terms of a parameter. I can tell all those parameters. That's not a problem. For example, learning rate is there, warm-up rate is there, right? And whenever you sample, there's some probabilistic probability values. So that's called, if I'm getting it correctly, that's called, I think what is called, this is called some warm, something like warm, what is my, exactly, some warm things there. So there's a lot of parameter, but the very good thing is those transformer models, they are very stable in terms of your learning parameters. So if you take my advice, if you're really trying to look for tuning, so try with the default parameters, which has been, uh, which for which that transformer model has been trained. There are very rare cases which we have to really go and tweak the parameters, all those kind of things, right? So I hope that answered the question. Again, objectively, the parameters can be learning rate, parameters can be a warm-up rate, all those things. But my advice should be not to play with all those things. There's a different parameters that's called, war make, consoft as function. Try to play with those, which is not learnable. That is just at the runtime, you just tune those parameters. Yeah.
Oh, thank you, sir.
Yeah.
Very well explained. So, okay, thank you from my side. Now, Millie, please continue. Yeah, Millie.
Millie?
Yeah. Okay, anyone have any question? No questions? Okay, thank you so much, sir, for such an enlightening session. Your expertise has made this session incredibly engaging and insightful. Thank you so much, sir.
Thank you, guys. Thank you. See you.
Yeah, thank you, sir.
Yeah.
Thank you, Vishal sir. Thank you.
So there will be a tea break of 20 to 25 minutes, and we will start our next session at 7:30.